me. So there's one that's called Why Great Employees Leave Great Cultures. The author is Melissa Daimler, and she's actually head of organizational effectiveness and learning at Twitter. It's in the Harvard Business Review online, and you guys can read it. But this article delves into the elements of culture and specifically how to meaningfully consider the value and importance of culture when building and maintaining a highly productive and innovative work environment. And the elements that she brings out that I've organized my talk around are behaviors, systems, and practices. And so a great culture is when all three of these particular elements are lined up and when the organization's espoused values. So there's a lot in that last statement there. That means you actually have to have values. And there are lots of projects that I've walked into where you're not exactly sure what the values are, what the goals are. So that's a first step that I'm going to talk to you about. So behaviors. What are behaviors? It's the creation of value statements and clear expectations. We heard about that already. I think Jen actually talked about that today in her award acceptance, which really resonated with me and I'm sure with many people in the room about setting expectations, I should say. The communication of value statements is very important as well. So once you've got them defined, communicating them. And then the enactment of value statements by leadership and by the organization. So you've actually, you got to walk the talk. And once all this happens, you know that you have a whole bunch of smart, very capable people at your disposal. So if you can get this done, if you can create some value sets, you can actually communicate them and enable people to align themselves to that. Suddenly you've got a lot of smart, capable people you can just let loose, and they'll do exactly what you need to do to reach the goals that you've all agreed upon. So I'm going to give you a little bit of a snippet in terms of what that means to me in terms of running analog projects. So when it comes to setting expectations, what, who, when, how, so that's what I'll talk to you about. So defining them. Identifying internal and external stakeholders is very important. I spent a lot of time thinking about that, and I'll talk to you about what that means shortly. I communicate. So communication is very important. To communicate these expectations, we do so early on, we do so often, and we also do so in something called just in time. So just before the event, as an example, I will communicate out safety regulations, things like that. We will connect internal and external stakeholders to the purpose and vision that you have agreed upon at hand and imbue them with an intrinsic motivation to see the project to success. This could be as simple as you have parked your 53-foot-long communications trailer, mission support trailer, in the middle of a small community in northern Canada. There are people that need to walk their dogs. Their dogs always pee where the trailer is. That inconveniences them. You need to go talk to them. You need to knock on the doors, or you need to enable part of your team to go and actually break down those barriers and communicate to people that this event is happening and why it's important, so that when they go there with their dog, they're like, oh, hey, Rover, this is cool. We need to go around. It's important, instead of grumbling their way through, because I can tell you those little grumbles can have a massive ripple effect. And those are the external stakeholders that I concern myself with, all the way from the permitting bodies to the cultural leaders of the area and understanding the cultural nuances and importance of that area, as well as the local, literally the locals, everybody that will have some sort of stake in maintaining the environment that you are studying. So some of the expectations, getting to the comment earlier around code of conduct, we have been setting those for our team for many, many years, because something that we have run into, which I'm sure many of you have as well, is that sometimes, and this doesn't just happen with the young people, in fact, a lot of times the perpetrators of this are not the young, it tends to be the more senior staff that come in, is they assume that a field analog is like a summer camp. It is not a summer camp, it is a workplace, right? So with that expectation in mind, you're gonna comport yourself in a different way than if it was summer camp. All of my camps are now dry. When I get onto the ship, the Nautilus, to go out to sea, they have made all of their ships dry. And sometimes, people have a beer or whatever, that's adult drinking, that's super fine. But I bring this up and maybe very, common sense or maybe a little uncomfortable, but summer camps, or if you're going away for some sort of retreat, you can drink, but we can't drink on the workplace, right? Especially when there are safety and logistical issues at stake. So that is something which, funny enough, sometimes people haven't clued into. So I make that a very clear, very understood expectation about all the camps that we have. And so around that, we have used over the years, it's actually in very, palatable, consumable language, something called the recognition of responsibility. We circulate this document here. It's gone through several evolutions since its inception at the Pavilion Lake Research Project. We now hand it out during all of our analog missions. And then Linda Kobayashi, who I've worked with for many years, who has been our logistics manager, brilliant human being. She loves spreadsheets, so I love her, because what she does is she basically hounds people until they have read this and they put their initials beside their name that they've read this document. And we talk to them about it, we have telecons about it, we help them decipher it so they understand the expectation as they walk into each one of our camps. The other thing, another expectation, something that has been a bit of a bane in many analog programs is publication. You spend a lot of time prepping to get into the field, then you go into the field, and then people disperse, and there are so many bits of knowledge that tend to get lost. You get the core papers out usually, but there's so much else that you've learned, so many other offshoots, ancillary benefits of that activity that have been lost. And that to me has been a real shame over the years, and something that I wanted to improve upon with each subsequent analog. So what we have done as well is put together the Basalt publication guidelines. We put this out early, we put this out often, and we put this out just in time, just before you're getting prepped to put together that special issue. These publication guidelines give everybody an understanding of the expectations of collegiality. You do not scoop your buddy. You do not send out your buddy's data to other buddies that are not part of this program. You cite your funding source. You include the people that have contributed to the program, remembering that, and this is common sense to me, but not necessarily to everybody, so we put this out again very clearly. When you have an analog mission where you have had the chance to gather up data, you have probably been reliant upon the logistics manager more heavily than you think you have in order to be successful as a scientist. So think about whether for their career it might be beneficial to put their name on your paper, and be open-minded to that and be generous, because it does actually have a wonderful positive ripple effect outwards when you do that kind of thing. So we put that perspective out into the open with our projects very early on, often, and just in time. Let's see here. The other thing I wanted to mention, just to back up, somebody said this to me they came on a reconnaissance trip with me, and were shocked with some of the things I had on the itinerary in a positive way. Not like, what are you doing? But what I do during a reconnaissance trip is I will go out and before even landing, identify as many external stakeholders as possible, as I mentioned to you early on, who those people might be. And then I'll go and meet with them one by one by one. I will take pictures of the places we're going to stay, that type of thing. I'll also ask them very directly, who do you think could shut us down? And people always laugh, and they actually find that to be a very fun question to answer. And it actually shows to them that we have experience in running into difficulties locally, especially when you're operating in areas of some importance to the local community. And they're never offended, they're always excited to actually consider that and then try and break down those barriers with you. So again, it generates intrinsic motivation with your local stakeholders, your external stakeholders that eventually get wrapped into the entire family. So there's a transition from external to internal. So all these types of things are being done very deliberately as we move through and set expectations. The other thing is we have to integrate different perspectives. So very purposefully, and again, these could be talks that we go on with for several different presentations, but there are various sensitivities that have to be taken into account as we move these projects in from multidisciplinary into interdisciplinary. So creating a safe environment for participants to express sensitivities early on. That can be anything from their food allergies to their sexual orientation to the fact that they feel unsafe in certain types of conditions. We want to be able to put that out in the open and allow people to have other people to come to speak about this openly and safely. That will help to create a safer environment. And we want to set the expectation that the environment is supportive of this. Inclusivity, it's just a word until you actually start to think about it and start to imbue the environment with that clear sense and that expectation of inclusivity. Zero tolerance for discrimination, for harassment, for bullying. we put those forward again at the inception of these projects. And we also try to state the purpose of making sure that these perspectives are integrated and these expectations are put out there. So one articulation of this purpose is that arriving and thriving on Mars, as an example, or the moon, will be an unprecedented endeavor for humanity. The way to meet this challenge is through a dimensioned approach, one that can only arise from convening people of different races, gender, background, and experience, and then enabling them to innovate at their fullest and collective potential. So we put that there, I put that out there a lot, so that it's anchored. We're not just focused on this project, but trying to use the project as a conduit for what we want to see on a grander scale. Communication, internal and external. Again, meetings. I get asked about meetings, like how often do you meet? Well, it depends on what kind of meeting you're talking about. So I'm giving you a simple example here. We've published on our meeting cadence and other papers, and I'm going to be putting this in our in this management paper as well. Meetings should serve a strategic or tactical purpose, and meetings should be budgeted for in your proposal. So people have to spend a certain amount of time on telecons or in person. They've got a budget for that as best they can early on. Technology needs to be implemented to support meetings. They should be enabled. Users should be trained. If you're not familiar with Slack, with Drive, with Zoom, whatever, those kinds of expectations around tech should be put on the table quickly, and then people should be trained up on it. The frequency. So as an example, what we do is we have a kickoff meeting. It's usually face-to-face. Once at the start of the project, we have alignment team. I'll talk about what an alignment team is in a minute. We do that monthly. We have all hands meetings, which are bi-monthly, and work area meetings weekly to bi-weekly. So you can set your own thing. This slide is simply to say, when you communicate, you have to have a plan or people will sort of drift off very rapidly, especially if your project is 4 to 5 years long. Also, each meeting should have a purpose that's understood early on. Of course, the theme will rotate around the meeting. But for example, to map A to A, so A, kickoff meeting is to enable the team members to share objectives, discuss work area organization, finances, and other related matters. When I think about it and abstract really what I like about kickoff meetings, it's that these human beings who are basically going to spend 92% of their time on the phone with each other, they get to come together and kind of sniff each other out for the first time, look each other in the eyes, realize that's another human being at the other end of the phone. You can't yell at them. You can't be a jerk to them. That's a solid, amazing human being, and we can get through this together. So that is one huge component of a face-to-face, especially at the start of a meeting, a project. B and C, alignment team, all hands meetings. So these are to report on what are called work areas. I like to call, instead of, basically the different sections of our projects have been called work areas very deliberately. And then we actually have alignment teams because what we're trying to do is make it clear that every person in our team has the capacity to innovate, to be a leader, to step up. But you need these people that will come together and be part of the alignment team to communicate as an intrinsic whole what some of the issues are that are being dealt with, what are the net outcomes of some of the work that's getting done, and then to align that again to the common stated purpose of the project. And D, these are research discussions that happen frequently within each work area, and sometimes they happen multiple times a day, multiple times a week. I think you've all had those kinds of meetings. So again, people understand the purpose, and we tell people often. The other thing that tends to happen in our analogs is, especially when we don't have a singular, type of analog. So you can have operation-focused analogs, science analogs. When you have analogs like what's supported, for example, through P-STAR, where you can bring science operations, and technology together, so you have a lot of people, again, in these multidisciplinary groups that to become interdisciplinary actually need to understand what the heck the other person's saying. We all bring a ton of acronyms to the table. We have common languages that we use within our work areas. You've got to cross that boundary, right? It's like crossing into a different country effectively with a whole bunch of different dialects. And so for science, what we did, for example, with Basalt, and we did this with other projects as well, is we created a dictionary, a lexicon of all the different, you can't really see it here, unfortunately, but it's like, what does alteration mean? What does different percent alteration mean? What does it mean to actually have crystals embedded within the matrix. What is the word to describe it? We needed that because it had to be translated to those that were producing the EVAs and producing the tasks associated with the EVAs. And so all that language had to be clearly outlined, defined, and then communicated. Ditto for the operations group. They created a whole lexicon of what an EV crew member is, what an IV crew member is, what an EVA is, and what different target regions are. Surprisingly, we spent several telecons defining what is a region, what is an area, what is a sample, a section, like all those types of things, because people disagreed a lot. And then with technology, many different terminologies, which, UDP, like what mesh networks, like what does that mean? But it's important for people to understand it, even though they're not necessarily setting up those mesh networks, so they understand the whole. Systems. So this is another component of what was brought up in that Harvard Business Review document. So building and organizing, oops, just a sec, let me back up. Let's see here. Building and organizing the team. So there are many possibilities, as I've mentioned. I use work areas and alignment teams to signal that there are key people who must help integrate our project. We're very clear about goal setting on a weekly, monthly, and by mission basis and by work area and so forth. And again, these are simply what we do, what I've done over the years, but suggestions to and examples to help you understand what these systems are. Decision-making processes. This is something that I will show you in a couple slides about how we actually try and anchor all our decisions very clearly in common purpose. And identifying talent and developing and enabling the talent, which is a form of reward. So we've had a lot of people start off with us as undergraduate students, as an example, and actually stay with different projects as they move along. They find that to be very rewarding. They find that to be important for their growth. Myself, as somebody that's had those types of people move through the system, it's been deeply rewarding to see these incredible people just kind of move through and become more and more capable. And that's something that I think these analog programs are very well suited to do. So enabling the components to interact and evolve as a collective is of paramount strategic importance. So let me just go to the next one here. Part of the systems that we set up, they can be in project management, much that the previous slide put forward and that I'll develop more in the paper. But then there's the whole component of systems engineering. So Matt Deans, who's on the line, really led some of the projects that I worked on, led the architecture development of bringing together all the different systems engineering pieces. Well, Jessica Marquez is in the room too. And they're familiar with some of these little images that I've put up. What we do in terms of our engineering is we have to put in place the decision-making framework for the engineers as they develop, as they integrate with the ops and the science community. And so we will spend a lot of time scripting the requirements for each different work area as they pertain to tech development. We will then spend a lot of time prototyping timelines, as an example, before they meet their full form in software, in software application. We'll also just spend a lot of time in front of whiteboards, sketching out the connections, as you see in the bottom left there, of how different components will meet together. I know many of you in the room are familiar with this. It's kind of, something you're like, of course, I do that. But there are also a lot of young people who are starting out that are on the line, and that I wanted to show them the type of rigor that can go into the development of our systems engineering. So let's talk about leadership. I have a few more slides here before I open the floor up. So aligning all of the elements of your program, the internal leadership. So what are the core work areas? Those are questions. These are questions that I ask myself. Again, I have only me as my sample size of one to put forward in terms of how I manage through these issues, but I look forward to, again, opening the floor to many of you. How do they need to be integrated? Who would be well suited to manage these work areas is something I wonder and then help to nurture through the group. What is the experience level of the work area team? How often should we meet? And what additional support will be needed to enable our team to thrive? So logistics manager, field safety manager, these are all things that I've kind of learned over the years become very important and that we should budget for at the get-go. When it comes to PI-ship, on a very personal level, I think it's important to ask, how will you lead your team? So this is for all of you, and maybe you've asked yourself various other questions, but for the young people out there, these are some things that I think are important to consider. Will you lead by consensus? Will you lead through hierarchy or other? And I think it's very important to be honest with yourself. What do you feel comfortable with? What do you think is best for the group? Can you actually do what's best for the group? What are your strengths? What are your weaknesses? What could you improve upon since your last at-bat? I have always a ton of things I could improve upon from my last at-bat. And I think, again, last point that I said earlier, super important to be honest. In terms of the next slide, this to me, and Jen actually alluded to this morning as well in her presentation, this to me is kind of sums up some of the utility, I think, of a PI. Striving to be a multiplier and not a diminisher. There's a great book by a woman who's actually local, and she actually has, you can read the HBR article as well. It's kind of a summation of this. It's called Multipliers. It's by Liz Wiseman. And the key message here is that smart leaders get more out of employees, can get more out of the employees that they have. So let me read you this passage here from her HBR summary. Most companies are adept at bringing in smart, talented people, but few companies put as much discipline into understanding how fully they are using the talent they've acquired. Many managers are so focused on their own ideas and capability that they shut down intelligence around them. I call these leaders diminishers. Yet other leaders seem to amplify the intelligence around them. I call these leaders multipliers. So for me, I hope I am a multiplier. I am sure I am a diminisher from time to time. Hopefully it's less than the multiplier component, but like it's a thing, right? And our egos get in the way. Our lack of time, our lack of sleep get in the way. But I think ideally, especially when it comes to these analogs, where they're so complicated, or any mission for that matter, being a multiplier with a whole bunch of smart people in the room, man, oh man, you get a huge bang for your buck. It also means, for me as a PI, that I need to remember that in my line of work, I have to be satisfied, deeply satisfied with delayed gratification. Okay, I know many of you in the room that resonates with you. Because I think the need for immediate recognition, while that's super nice and awesome, it sort of distracts from attending to the greater goals at hand. Okay. So, last thing, practices. Are there clear, repeatable decision-making processes in place in your group? Are these processes dependable when the project needs to grow, pivot, or realign? As an example, again, an example from our groups that have developed, this has been developed over the years, but was developed early on, probably in '05, and then refined when I first started Pavilion Lake. So our decision-making principles for all of the analog projects that I've had the privilege and joy of leading come down to these three very basic things: safety, environmental stewardship, and then research. So there's a hierarchy here. Everything we do has to be safe. Next thing, are we actually taking care of the environment that we said we were going in to study, not destroy? And then the next thing is, let's make decisions that come back into our research and meet the higher level goals of the research. And that research is represented by research traceability matrices. Not every team does this. We always do this. It helps me when I get lost in our, on our journey to realign. This is built by each work area as almost like a stovepipe and then integrated. And in the case of basalt, this included, the research traceability matrix included, of course, as a subsection, a science traceability matrix, which many of you have built for different missions. The purpose of an STM or an RTM is that it anchors each decision in articulated and democratized goals. Okay, that's huge because we do get wayward, and then this offers a Hansel and Gretel way back when conversations get hairy. And they get hairy. So again, some final thoughts. This was a very North American presentation, totally admit that. The management practices, leadership styles, sensitivities, and so forth will differ around the world. And we are around the world with this working group, but there are undoubtedly common cross-cutting themes. So the purpose of this as a kickoff was to find similarities, to find differences and nuances together and explore them, as I think this process will unlock insights for each of us to act upon in our collective interest to grow and develop the analog community. And that is it. So, thanks. Thank you for listening. The other thing I wanted to mention is that I just read this awesome book. I can't remember the name of it. Well, I read it a couple years ago, so you have to forgive me, but I can give you the name. It was all about the history of Apollo science and the management of that through the agency, through bringing in USGS. And what was fascinating to me is all the management issues that we deal with, that we hear about in the hallways, that we are living through, the creation of STMs, aligning people. They dealt with that already. Same thing. People were worried that their bread and butter was going to get taken away and given to someone they didn't like. And so, again, delayed gratification, putting this whole journey into perspective. We'll get through this. I think we just have to kind of figure out a way which is collegial through it. That's kind of the purpose. Okay. What do you want to talk about?
Take questions? Maybe
Yeah.
online first?
Yeah, let's do it. Take questions or suggestions on other project management items you want to noodle on or anything else. I'll take notes. Go ahead.
And we have about 5 minutes until the next session in this room, so we'll go till we can't.
Thank you. I just want to tell an anecdote that it resonated exactly what you were saying, your style of management. And this is my alarm that I need to take off because I'm chairing this, this next talk. But I just want to say that from my point of view, I was the safety, I'm a physician, so I was the safety diver officer for an expedition that was in the middle of nowhere in Turkey. And this is for an archaeological excavation that was 2,500 years old. Okay, we have people from all over the world coming in here and to that site, which was very remote, as I said, and difficult to get access to, food, service, anything. Then what happened is, I cannot explain you what happened exactly because then I will get in trouble, but we had contamination of the water, okay? I was the one that figured it out because I had that training, but everybody was getting sick. And we were all getting sick. So you know what I said to them? Because they were like paranoid, or we're gonna die. And I said, we're going to find the answer, okay? And if we die, I'm dying with you. But what happens though is, I let them loose. I could take care of the very sick people because I knew I had the capability, but I could not take care of everybody. 60 people, okay, on board. So I let them loose, and I told them at lunchtime, because everybody is going to eat, right? And if I tell one person, they go off on a tangent. But I wanted to catch them all at the same time. And I said, we are all in this mess, poo-poo here, but I am dying with you, so I'm not going to leave you alone. So what happened is that message was so clear in their mind, and I said, you've been trained, you are intelligent people, you come up with answers, I'll take care of this thing, but let's go work on this safety protocol, right? I cannot imagine, they came up with so many answers and so many tricks that I could not have done it myself. So it was amazing to see the power of letting them loose, and as competent people that came there for a purpose. And then we resolved that in 2 days. 3 days was my cases that were really sick, that I couldn't take them to a hospital. But I was about to call a chopper from the National Guard, from Turkish National Guard, to evacuate, okay? So imagine that risk, right? But since we're all on the same boat, like I said, we are going to take a mission. And so at that time, the critical thinking skills is very important. And everything that she mentioned resonates with me all the time, because I took that risk 3 years in a row. Okay, but if the first year I had not made that decision, we were not going to make it. And the reason I cannot disclose so many things is because then we have National Geographic. And National Geographic was going to give us, we were on TV, and we're also on the special issues of National Geographic. So can you imagine that? So I understand exactly what you're saying, and you probably want to be a multiplier, that's all I'm saying.
Yeah, does anyone online want to chime in while we move the microphone around?
Yeah.
Yep, go ahead.
Okay, is a I really appreciated the presentation, and I would say that we do share everything. I mean, even if from the Italian perspective, the way which you have presented how to manage an analog situation is exactly the same. And so completely sharing everything. Let me just add one other level of complexity that we had when we ran tests having industry on the field and in view of ExxonMobil's mission, so with a very tight schedule. At that point, the schedule became is the driver of everything else. Of course, safety is a prerequisite, and all the rest. But when you have hardware to be tested on ground and industry guys on the other side of you, then schedule is really the mantra that every morning at the briefing you're going to listen to.
This is Jessica. I just wanted to thank you. That was great. One of the things that I am also seeing is, I'm from NASA, so safety is always first, because as soon as you have that first mishap, that analog will be gone forever. And I'm seeing when we have some analogs that go on for a really long time, people get complacent. And how can we creatively keep energizing the people that are managing it, because their teams are getting smaller, they're having more responsibility, and so basically have to enforce the safety perspective with less people. And it's, I think it's, part of it is economics, there's just less people. But that I think is an interesting challenge for the longevity of maintaining that safety culture. And I know that we repeatedly do it like at the deployment, or like at the end. I know you stand up and you're like, we're at the end of the mission, almost at the end. This is the most dangerous part because we're all tired. But I think if you look at it, step back and look at it from like maintaining an analog over years, that's the same thing is happening.
All right, we'll have one more and then
Hi,
we'll do a
could I-
discussion. Yep, go ahead.
Am I able to just chime in with a comment? So my name's Bonnie, and like I just said, I'm a doctor, having worked in desert analog missions. And just following on from that comment that was just made, so I'm part of a panel of a number of doctors from different analog platforms, and we are trying to work hard to create an affiliate group of the Aerospace Medical Association to provide those resources and that support for any group that wants to dig into it for that medical support and safety aspect. It's still a work in progress at the moment, bearing in mind that there's a variety, a real spectrum of analogs out there from, like you say, NASA with all the funding and the resources. There's much smaller groups who are largely volunteer and run and based on people's kind of best wishes. So we're trying to, that's something that's trying to be established with the support of ESA and NASA at the moment.
That's great. And it's great to hear there's a lot of interest in the medical side of things too, so we can
tell the
Okay.
speakers about the 12 minutes and one. But we can't delay in case, because then the whole thing gets pushed.
No. So we'll give them 12 minutes?
Yeah, then
and
give-
then
they'll get
we've
a
got
1 minute
1 minute
warning.
warning.
And then a couple of minutes for questions and transition.
Okay. Not slept well the past 3 nights. I'm used to waking up and dealing with a 2-year-old. You'd think it would be easier. That's what I thought, but it's just, well, my wife's also pregnant, and so she keeps the house at like 68 degrees right now. And so I'm saying with Brent, and we agreed on like 70, 71. I don't know if that's what it is. I'm not sure. He's like, I can't sleep in a meat cooler.
It's a
My wife would not be sleeping in our hotel room if.
I'm going to shift people out.
okay.
Yeah, I was looking forward to sleeping. How have you been doing?
Good. I'm glad we fixed this thing. 'Cause I wanted it's okay. I want to have after this, have a debriefing with everybody on Reveal's team. 'Cause I've been organizing this conference. I know I've been seeing, things. And I want to have like a management approach team now. Okay, so I'm gonna call a meeting soon.
So I've got time. Let's
Okay. All right, so we're going to start this session. This session is going to, first of all, we're going to have the timer is going to be 12 minutes, and we're going to give you 1 minute warning when it's almost close to the times, and after that, then we'll cut you off. Okay, just make sure that you have, otherwise we run late. So this session is called Crude and Robotic Space Activities. This is an important session because probably is what I like, the things that I like the most. But our speaker, the first speaker is Zach Zievers. He works with our team, actually with Reveal's team. He's the one that does a lot of the work that he's going to present. And I am very proud and honored that he has decided to give this talk and the applications of what is going to, how useful that's going to be. So thank you, Zach.
Thank you, Esther. I generally like to walk around a little bit, so I'm going to do my best to stay right here and talk into the microphone. But yeah, so as Esther talked a little bit about, I do work on composites, and what we're trying to do is solve some of the problems, the challenges that present risks to the astronauts and equipment in space applications. And so we know a lot of these, but I'm going to point to 2 and focus on those, and then I'll get into some of the details of our work. Let's see. So the first one that I want to talk to about, because it's something that's not generally thought about in terms of space danger and hazards, is static charging. And this is actually, there's a history within NASA and the ESA where we've actually had missions compromised and even catastrophically failed because of static charging. And generally speaking, for the sake of time, I won't go into a ton of details, but these end up causing shorts at things like solar cells, batteries, electrical components, things of that nature. And so if we want to get rid of these things, we need to develop ways that we can dissipate these static charges and do something that's more controlled with those charges. And just to give you an idea, we deal with this in certain aircraft applications, especially things that fly at high altitudes, at high speeds. And something like a commercial fighter jet would have an anti-static shield coating. It's a polymer-based coating, and those are about 100 megaohm coatings, give or take, so it's nominally. Another one is, of course, health hazards. Radiation has a variety of negative effects on the astronauts. And we are just still learning a lot about this. And there's actually a recent paper that looks at heart disease. And there's suspicions that some of these lunar astronauts are having problems from the Apollo program, are having problems with heart failure or heart disease. So this was published in Nature a couple of years ago. And so the take-home message here, I know everybody knows that radiation is damaging to people, but the takeaway here is that these are big issues, and if we're going to survive for long-term colonization or long-term missions, it's imperative that we figure out a way to remedy some of these problems. And so if we're going to block radiation, there's 2 main ways that this can happen. When the first is to just absorb the radiation, and generally what happens is the material is going to form some type of radical, And heavy metals and things like that, it's not a big deal. They've got a much more large nuclei and electron field that they can do, electron cloud that they can kind of do different processes to deal with these charges. Some polymers can deal with this, but, and so I mentioned polysulfone a couple times in this talk, which is why I mentioned it here. The more common way that we think about blocking radiation is just by putting a lot of hydrogen between the source and the target. If you've ever done any type of radiation exposure experiments, you might see big chunks of polyethylene actually between your sample and that. And then we do that to tune the energy of the radiation coming in. This is also one of the reasons why we would submerge a nuclear reactor, is because it blocks in water, and that's because it blocks a lot of this radiation. Liquid hydrogen, you'll see a lot of applications where liquid hydrogen will be used on spaceships to block radiation, or concepts, I guess. So if we're going to do this, I'm not going to sit here and say we should build our spacecrafts out of plastic bags. This is obviously going to be a multi-layer approach, and so just keep that in mind as I go through this. But what I'm specifically going to talk about, I'll give this one shot, is this conductive layer top, this top piece. And this is, you can imagine this is going to be reinforced with a fiber reinforcement, and then there's some backer layer, and that would be tuned depending on the application. If you're on a spaceship, you can afford to have a little bit more mass, whereas if you're on a space suit, if you're thinking about space suits, it's got to be a lot thinner for weight considerations. So as a base, just to give you an idea of what our approach is going to be, we're going to look at thermoplastic materials that we can scale. We're not trying to do anything that it's $1 million for a gram of material. That's just not practical if we're going to have a long-term sustainable solution. And so two materials that I'm going to talk a little bit about are polyethylene and polysulfone. These are kind of on opposite ends of the polymer performance spectrum. Polyethylene, you've seen that. I'm sure you have a ton of it at your house. Polysulfones are much more unique. They're used in medical applications and have been used actually to build satellites and things like that. They're much stronger. And then we're going to take these things that are both, most of these thermoplastics are insulating, especially ones that can be synthesized at scale. And we're going to reinforce these with a material called reduced graphene oxide. And I'm going to show a little bit more about this, but the big problem with graphene, or reduced graphene oxide, is that it likes to aggregate. And so kind of the linchpin of this is going to be dealing with that aggregation and controlling the dispersion into a polymer matrix. And so just to show you what that might look like, if we were to go through a normal melt compounding process, so this is what would happen if you were going to do injection molding or something like that, you would see the exact same effect. And all I'm doing here is just heating this up, blending it in a compounder, melt pressing it into like a pancake. This is a thin film. It's only a millimeter or so thick. And we can see it's just not very pretty. You see this large area of aggregation here, and that's just, the graphene's just not moving around. It does not disperse into the polymer matrix. So even when you make a sample or something like that, these aggregations are stress concentrators and they cause the material to fail prematurely. And so if we're going to do this, we're going to have to modify the graphene. And that's, as I talked a little bit about, or alluded to earlier, that's kind of the linchpin of this project, and what the bulk of my time was spent on in the first couple of years. And so I'm not going to bore you with a bunch of chemistry, but I just want to show you, we take this reduced graphene oxide, there's some functional groups. I'll show you a quick picture in case you have some interest in the chemistry. But we can take these things, we pre-mix them because these graphenes it's a very light powder. It's very much like normal graphene or nanotubes. You don't want to breathe it. So we pre-mix it, and then we put it into a melt compounder, and we can make samples. As to show you a little bit about the chemistry, this is not pristine graphene. Pristine graphene is very expensive to make. It's not something I would think you're going to want to make a spaceship out of. So reduced graphene oxide is much more scalable. I can do this in a 100 mil round bottom, or I can scale it up to, right now I'm doing it in a 4 liter round bottom. So it could easily go up to a thousands of gallon scale. And just to talk about the properties, again, I'm not going to go through a bunch of chemistry, but before and after my modifications, if we look down here, these odd numbers are actually reduced graphene oxide that's not been functionalized. And then the even numbers are reduced graphene oxide that has gone through my chemical modification process. And we can see that in a variety of different solvents, these things are dispersing. And that's one sign, at least, that we're preventing the aggregation and allowing this material to do things that we want it to do. It's much more processable. And then just to give you an idea of the conductivity, this is just using a 4-point line probe. We can see that graphite would start out at something like 3,000 centimeters, or Siemens per centimeter, Reduced graphene oxide takes a big hit because, again, it's not a perfect graphene sheet. The basal plane has defects. But then upon modification, we only take a slight hit in conductivity. So we're doing this, we're gaining a lot of processability and only taking a small hit in the conductivity, which is very nice. I'm going to talk about 2 different melt sample preparation procedures, and I just wanted to make sure that everybody knew what I was talking about. One is melt compounding, like I showed you earlier, using an extruder. We take these things, we mix them, we can extrude that material and then press it. You could injection mold, anything like that. Another is melt lamination, which is a little bit weird, but you can imagine having a film and then taking a polymer, a thin layer of the graphene, and then you take a thermoplastic and actually press it down into the graphene. And then what it'll do is it'll soak up that graphene into the top of that material, and you get a gradient effect. And I'm not going to talk too much about that gradient, but we're using this for a very particular measurement that I want to talk about. So the melt processed samples, or the melt compounded samples, these are just some more samples like I've shown you before. We see this is the, just a little like that, it goes dark here. So I'm just going to say on the left, you see the unmodified reduced graphene oxide. On the right, we see it's much more uniformly black. So these are made with the exact same polyethylene, and the only difference between the reduced graphene oxide is one has been functionalized and one has not. And so just immediately in the appearance, you can see a big difference. And then obviously, or not obviously, but shouldn't be too much of a surprise to the material scientists in the room is the one on the left is not conductive and the one on the right is. That's because it's well dispersed and you've got a pathway to move these charges through the material. Some of these results are actually from a version 1 of this graphene modification scheme, but I want to show you that this dispersion is not just aesthetically pleasing and not just for conductivity. We actually see big differences in how these things fell. And so on the top left, you see a material that's been modified with reduced graphene oxide, and it has a much different failure mechanism than the one on the bottom left with the modified graphene. And that's what you're seeing in the bottom left is a thing we call necking. And so if you pull the material, it behaves like a plastic. And it actually turns white. You can see here at the break, see if I can point to this. This white here, you've seen that with a plastic bag when you tear it. That's actually the crystallization of polyethylene chains. And then if we look at this stuff with cross-sectional electron microscopy, we can see big differences in the fracture interfaces. And this is just a clear sign that we're having we're doing a much better job at preventing this aggregation after our chemically modified graphenes. And so one more just little bullet point from the same preliminary study. We can see differences in the moduli, and I didn't want to lose everybody in just a ton of data here, but we can see that the performance of these things actually goes up. The mechanical properties get better after this modification. So this, again, just reiterating that this is a big result that we're seeing here. And then, so, another thing is I've talked about radiation, and that can obviously have an impact on humans, but it can also have an impact on people. So if I'm going to propose a material that relies on graphene to modify the properties of the thermoplastic, we need to be sure that graphene is going to survive the radiation as well. And so, excuse me, what we're going to do is use the melt lamination technique I talked about a little bit about briefly, and we make a sample that looks, we see a representative sample here in the bottom left, and you can almost see a bilayer approach, and it's hard to tell in this picture, but this gap right here is not all the way through the material. That's just a result of the mold not releasing, or the sample not releasing from the mold very well. But the point is this top layer is graphene, and the bottom is mostly white. So if you were to look at this thing and hold it in person, you'd be able to tell that the bottom is neat polyethylene, the top is our modified graphene. You can't actually do this with the reduced graphene oxide that's not been modified because there's no way to form a neat monolayer of the graphene in your mold. And so what I just wanted to show you is that it's hard to get a conductivity value because to do that we need to know the thickness of the sample. However, we get sheet resistances that are comparable to, that are much more reasonable in terms of conductivity. And this is more than sufficient, this value here of 2.6 times 10 to the 1 ohm meters. That is more than sufficient to dissipate charges. So this could also be, if you had an application where you needed a very high conductive surface for some particular application, you could easily do something like this on a large scale. And this would work with injection molding or anything like that where there's a mold involved. And so we were fortunate enough to have a piggyback experiment at the NASA Space Radiation Laboratory where we were able to simulate GCR and SPE events. We do the best we can. It's not exactly what you would see in space, but they have a synchrotron source. It's definitely not a source that I would want to sit in front of. But I'm happy to put my samples there. This 80 centigrade dose that we exposed our samples to was chosen because that simulates what you would get from a round trip to Mars and back, just from background events, not something, what we know about the radiation at least. Okay. And if we look at the conductivity of these surfaces before and after, excuse me, before and after the irradiation, we actually don't see that much of a change. My error bars here are missing, and I apologize for that. But these things are very consistent. We nominally don't really see a difference. There's probably more error in where I'm actually taking these conductivity measurements than in the measurements themselves. And while this is only a preliminary result, we actually just got this a couple weeks ago. I do want to say that this is exciting because these things are still conductive, and there's no way that this graphene would still be conductive if it was breaking down. It's all about maintaining that conjugated basal plane of the graphene. And so in conclusion, and some of the future plans, we talked about how this multi-layer concept, was our original approach, but we ran into some problems using the reduced graphene oxide that caused us to develop a method to to chemically modify the graphene so we could control the dispersion. And not only have we been able to successfully do that in a scalable way, but we've also been able to show that this simulated radiation doesn't seem to have a negative effect on the graphene itself. And so now what we're doing is actually coming into approaching more the engineering stage of the project, where we're beginning to reinforce these things with fibers, as you've seen here down on the bottom right, and then look at more the detailed mechanical properties of how these composites would behave under different applications. I would like to thank the Survey committee for organizing all this, organizing all these great talks, for research funding, my colleagues who are part of the Reveals program, as well as a few people that have helped me along the way, learning new techniques and making new measurements. And with that, I'd be happy to take any questions. Excuse me.
You're not allowed to have no questions. Can you talk a little more from the point of view of the thickness that you were thinking you would need, depending, very interested by the results at the end on the shielding aspect for radiation. I didn't get a sense for how thick, and you were talking about building it into the spacecraft. Can you?
Right. So that's a good question. And the way I think about this is you want to try and mitigate a lot of the background radiation. I'm not sitting here going to tell you that polyethylene is going to block a galactic cosmic ray or a solar particle event. But what we need to be able to do is rely on prediction technologies to be able to see that coming and find some other better means of shelter, such as a regolith cave or something like that. There's all kinds of concepts for that. But I do think that you see a big difference if you go to even just a very practical example that I can give you to keep away from big numbers. If you go to the Space Radiation Lab, what they use is about 10 centimeter blocks of polyethylene, and it can drastically reduce the energy of the radiation coming in. So I think from just thinking about it, practically speaking, in a spaceship, you might see something that on the order of inches thick, 6 inches thick, especially around like the habitat. If you had a shelter in a spaceship, maybe you could have a thicker, room shelter that has 10 inches or so of this polyethylene. But obviously, that's not practical for a spacesuit. Yes.
So maybe I'm asking a question that would take too long to answer, but I'm not getting how the conductive properties of the graphene are reducing radiation?
They're not. They're two separate things. So.
That is not, okay.
No, we wanted so for a lot of reasons, there's advantages to having a multifunctional material. The key here is that we want to be able to block radiation as well as having some means of dissipating static charge and protecting from micrometeoroid impact. There's a lot of different things that we're hoping these materials can do. But the point here is that we want to be able to, instead of having, I think the current spacesuits have something like 17 layers of materials that are woven together in a spacesuit. It makes it rigid, it makes it hard to manufacture. It's certainly not something you would want to work on Mars or on the lunar surface. So if we have simpler materials that are multifunctional, it gives you a little bit more control over repairs and design and actually implementing the material itself. So.
The abstract does a really good job of explaining why you'd want something to conduct. We're going to have to move on.
Yes, yeah. Okay, the next speaker, Next speaker is Donald Hendricks. He's going to be talking about these generating more analogous lunar regolith.
Hey, thank you everyone for being here today. So basically the purpose of my work is to try and understand the health effects caused by exposure to lunar dust. And so in order to do that, we have to acquire better lunar regolith simulants than what we currently have now. And we have to do that because acquiring real pristine lunar samples is very difficult, especially in the quantities that we need in order to do our studies. So basically what I'm doing is I'm taking JSC1A, which is a lunar regolith simulant, and I'm trying to improve it in order to be able to do reactivity and cell toxicity studies, in order to be able to see how these samples might affect people. And we need a lot of it in order to do multiple studies. And so what we do is we take the JSC1A and we use a simple reduction method described by Allen et al. 1994. And then what we do later is we measure the reactivity or the OH radical generation. I'll talk a little bit about that later, of both the reduced and non-reduced JSC1A. And I also present a little bit of data regarding the cell death caused by reduced and non-reduced JSC1A. And so we're starting with JSC1A because it's very widely available. So JSC1A was developed in order to aid in engineering and resource utilization projects related to lunar exploration. It was supposed to simulate the Mare basalts, but it doesn't do a very good job of that. And so, but there are positives and negatives with JSC1A. So some of the positives are that the grain size, or the angularity, grain size, the specific gravity, and the glass content are pretty much on par with lunar regolith. The electrical and thermal properties also match up pretty well with lunar regolith, so it's really good for engineering applications like rover testing. But there are, of course, downsides to JSC1A, primarily regarding the mineralogy and the chemistry of it. So there's a fair amount of clay minerals present in JSC1A, and since there's no aqueous alteration on the moon, you wouldn't see any clay minerals present in actual lunar regolith. There's also a large proportion of oxidized iron in JSC1A, whereas in lunar regolith, you either have Fe2+ or Fe0. And the biggest drawbacks are that there's no agglutinated glass or metallic iron present in JSC1A, whereas it's very common among actual lunar regolith. And so what we do to try and make JSC1A a little bit better is we try and reduce it. So we're trying to add metallic iron to the surface of JSC1A. And so what we do is we take about 3 grams of it, we add it into a glass sway boat, and we add it around there in the middle of that silica tube. And then we put that into this furnace right here, and then we heat it for 15 minutes at 900 degrees C. So when that's done, we let it cool down, we remove the JSC1A, and then the first thing we notice is that it gets darker, and this is due to the formation of metallic iron on the surface. And we repeated this a total of 3 times on 3 separate occasions. And this is what we got. And so basically these are all just JSC1A grains all over, and these blue arrows are pointing towards iron metal blebs on the surfaces of these grains. And this is very similar to what they observed in that Allen et al. 1994 paper, so we were able to successfully reduce JSC1A and add some metallic iron to the surface, as is common among the lunar regolith. It's a common characteristic among lunar regolith. And so after that, what we do is we measure the OH radical generation, or the reactivity of our reduced samples, and our non-reduced as well. And the reason we look at OH radicals because it's known to be hazardous to biological species, and so it's important to measure the OH radical generation of our samples. So the way we do that is we use a technique called electron paramagnetic resonance spectroscopy, or EPR spectroscopy. And so what we do is we take about 200 milligrams of JSC1A, and then we incubate it using a inorganic molecule called DMPO, and that will trap any of the OH radical that is made by the JSC1A. And then what it does is that it forms this stable compound that can then be measured by the EPR, because the OH radical cannot be measured by itself. It has to be attached to something more stable. And so what we got out of it was the results on the next page is that reduced JSC1A is way more reactive compared to non-reduced JSC1A. So here on the y-axis, we have the amount of OH radical being generated. For the non-reduced sample, we're only making about 1.8 micromoles of OH radical, whereas for the reduced, we're making double that. We're making about 4. So it seems that heat treatment and reduction of JSC1A and the formation of the metallic iron on the surface is leading to much greater reactivity compared to non-reduced JSC1A. And here we have the same 2 graphs here on the right, But now we're comparing it to some pure mineral phases that are found on the lunar surface. So here we have olivine, augite, and labradorite. So that's part of an early project I did a couple of years ago, where I looked at various pure mineral phases and tried to measure the OH radical generation potential of each of them. And so it seems that reduction of the JSC1A and the formation of that metallic iron causes a huge spike in reactivity, even compared to some of these iron-rich silicates that are commonly found on the lunar surface. And in that work, we found that iron-rich silicates are the most reactive of minerals compared to pretty much anything else. And so here we have some data obtained from our colleagues in the Department of Pharmacology. And so basically what they found is that here we have our JSC1A that's not reduced, and here we have our reduced JSC1A. And so the y-axis is the number of cells that have been counted after a treatment. So we have here our control. And for our non-reduced JSC1A, they counted about 100 cells. And for the reduced, they counted around 50. So it seems that the heat treatment and reduction, again, is not only leading to huge increases in the reactivity, but in the toxicity as well. So here's some results presented by Wallace et al. 2010. And so here what they did, so first we're going to focus on the graph on the right, or on the left, excuse me. And what they did is that they measured the reactivity of a nanophase iron simulant represented by this black bar right here. And they measured it with one of their batches of JSC1A represented by this gray bar. And this little bar over here is amorphous silica, so the silica that they used in this sample, but without the nanophase iron. So it seems that the presence of this nanophase metallic iron is leading to huge increases in reactivity. Unfortunately, they didn't measure anything quantitatively. They just did everything in arbitrary units. And so something that we can do that's pretty interesting is we can then compare to our results. And so basically, if we were able to plot our JSC1A here, it would come out to somewhere around here. And the reason we can say that is because their JSC1A came out to around 2,500. And if the reactivity of our JSC1A doubled due to reduction, then that means if we were to plot ours on here, it would be around 5,000. And so on this graph on the right, so this is also work that they did, our JSC1A would plot around here. And so as you can see, these are all Apollo 16 samples. So our reduced JSC1A so far seems to mimic the reactivity that of Apollo 16 samples. And so this kind of shows sort of the work that needs to be done in order to improve or to continue to improve a JSC1A, because since JSC1A is supposed to be a MARI simulant, this should come out higher. It should come out up here with all the other MRI samples. And it's not. It's coming out around here, so it kind of just shows that there's still more work to be done. And so for our conclusions, we were able to take JSC1A and successfully reduce it and add metallic iron to the surface of it, just like they did in Allen et al. 1994. So we were able to do multiple hydroxyl radical measurements with little errors, so we're pretty confident that our methods for measuring the reactivity are pretty good. And we found that reduction of JSC1A adding this metallic iron to the surface causes the reactivity to double compared to that of non-reduced JSC1A. And it also seems that metallic iron leads to significantly larger cell death compared to non-reduced JSC1A. So this has a lot of implications in terms of lunar dust, since lunar dust has a lot of metallic iron present in it. And we also found that reduced JSC1A with metallic iron, again, generates a lot more hydroxyl radicals, much more reactive compared to minerals like olivine and augite. So for future work, what we want to do is we want to take these methods and be able to use them on other samples. And so we want to take something, say, like, let's take olivine and let's reduce it, and then let's test how reactive and toxic it is, and then let's compare those results to the Wallace et al. 2010 work and see how well it matches up with actual Apollo samples. And something we also want to do, too, is we want to see what effect heat treatment alone has on these samples besides just the reduction. So let's remove the H2, and let's add something like argon, and let's see how the reactivity and toxicity might change with just heat treatment alone. And something we would also like to do, too, is we like to add or try to obtain this nanophase iron simulant and try to, let me go back real quick. and then try and maybe get some similar data to what they have here, and maybe change this y-axis from arbitrary units to actual OH radical generation, and then we can then more effectively compare to what they got over here for the reactivity of actual Apollo samples. And with that, I'd like to thank all these great people, and I'll take any questions you may have. A lot of questions, sure.
Have questions? Let's
No,
move
there's
this
too many
along.
people.
I have a question for you, but I'm going to wait for the public. I saw your hand going first. So.
Okay, Dan Britt, University of Central Florida. I can tell you why your reduced sample got closer to the highlands soils than the Mare soils is because the San Francisco the volcanic suite that you got for JSC1 is actually erupted in a continental area and is way more feldspar rich than what you're going to find for Mare samples. The real question I have is why use JSC1A at all?
So,
There are much better simulants that are a lot closer to lunar mineralogies that aren't full of, for things like calcium, which you don't really want and might affect your reactivity.
yeah, so we started with JSC1A first just because like that's kind of what we had to start with, but we definitely want to go beyond JSC1A.
Well, if you'd like a free kilo of much better simulant, give me a call.
Sure, yes, we were definitely considering doing that for sure for our next step.
The first one's free, yeah.
I also wanted to just give a plug for another collaborators that we work with who make their own lunar simulants. They're kind of non-NASA, and they have a Mare simulant and a Highland simulant, both of which include agglutinates. Their physical characteristics are much more realistic. So if you'd like to chat, I could give you their contact information. They would also love to be on your list of
Yeah, definitely.
Regolith
No,
simulant,
if you guys have
sources.
things that are better, definitely, I'd
Yeah.
love to get a hold of it.
We have time for one more question, just one more. No? Yep. That's okay, it's your question.
I know the answer, but what relevance does heating these samples to 900 degrees Celsius have to the surface of the moon? And is the nanophase iron that you're forming anywhere near the abundances that you would actually find in the lunar soil?
So the abundances, we don't have a clear answer on that yet. I want to try and get Moss-Bauer measurements on these and try and see if the amount of metallic iron is adequate. I'm sorry, what was your first part? That question?
Why? I mean, the lunar surface is heated to 900.
Oh, okay. No. So basically, our main goal with that is to try and get the metallic iron. We're not trying to really replicate the actual like vaporization and the formation of the agglutinates. We're trying just to get the metallic iron to see what effect metallic iron alone has on the reactivity and toxicity.
All right, so, thank you. Thank you. I was just waiting for Dan Britt to see how long was it going to take for him to say, use the Exolith lab. So it was kind of funny. All right, so next talk, and it's funny for me too because when it gets to over 50, you need glasses. So before I couldn't read the exact title of his talk, so apologize for that, Donald. But next one is Mark Cohen. He's going to talk about lunar daytime, architectural and behavioral experiments on lunar habitats. So thank you.
Thank you. The purpose of this talk is to address the issue of what is a good design for a space habitat versus what is a bad design for a space habitat. How do we know the difference, and how can we determine that in a way that has scientific validity? So traditionally, the limitations of habitat analog research, particularly human behavioral research, are the difficulty of producing scientifically valid results. Historically, habitability researchers have been limited to qualitative surveys and questionnaires. What this project, Lunar Daytime, will demonstrate is the efficacy of developing a modifiable environmental analog as a behavioral laboratory that can produce empirical, measurable, and quantitative data sets. So the reason is that researchers must be able to make and control changes to desired independent variables in the physical living and working environment. That means to change physical features, architectural plan and design features of the habitat to see how it affects crew productivity, crew sense of well-being, crew health, and so on. So, the purpose of Lunar Daytime is to overcome these historic limitations through the modifiable habitat, to measure effects on crew behavior, where the changes in the environment are changes to the independent variable, and the effects on crew behavior, mood, and performance and productivity constitute the dependent variable. So why do we call it Lunar Daytime? Because we are aiming at 14-day surface missions on the moon. Because once we actually do land crews on the moon for hopefully longer durations than Apollo, they will be limited to 14-day visits until we have a nuclear power reactor available to keep the power on during the lunar night. So therefore, Lunar Daytime, 2 weeks. Another advantage of that is that if we're doing 2-week-long simulations, we can get many more runs for the same amount of money compared to saying, okay, we've got to do this for 9 months because there's some concept that all space missions are really long duration. So that's another advantage. Many more runs, much larger N. So there are many potential variations in interior architecture that we would be able to test and do different runs with different interior configurations. So there are 2 major objectives here. One is to create a space habitat analog research facility specifically designed to accommodate experimental modifications in the physical and perceptual living and working environment, and to demonstrate the ability of this environmental behavioral laboratory to investigate and address the critical factors that play important roles in human health and well-being which is an isolated and confined environment. So our goal here, short term, is to build a module as part of the multipurpose research station at the University of North Dakota. The MPRS currently consists of a 5-module laboratory human planetary habitat analog complex built from 2 NASA EPSCoR grants, and I was served as a consultant for the habitat design on the first EPSCoR there. And we seek to expand the existing simulation facility as the most efficient path for realizing these near-term goals. And the addition of this 6th module will accommodate a range of spatial and visual experimental configurations to address habitat and psychosocial factors driving from the design. So this is a view of the early phase of the first EPSCoR grant, where the university built this analog habitat to simulate an inflatable with these space truss elements holding a rigid frame around which the inflatable was attached. And this was a view of the first deployment exercise they did, which I believe was the summer of 2014. And or in 2014 anyway. The integrated habitat system incorporated spacesuits, suit ports for my patent, and the rover analog. So this is what it looked like in January of this year with 5 elements. The original inflatable simulated habitat is the one in the largest one in the center. And so we have put together several hypotheses as examples of the types of investigations we would pursue. Hypothesis 1, the privacy of sleep quarters. Now, a lot of these things people will say, this is just common sense. Everybody knows this. But in fact, NASA does not act like we know this, like this is common sense in a lot of cases. And so the hypothesis is that providing individual private quarters will produce better outcomes, such as lower stress, reduced interpersonal conflict, higher well-being, more positive moods, more restful sleep than shared or common sleep quarters. And we would test multiple different configurations. Hypothesis 2 is windows. That digital display windows will provide reductions in stress and the sense of confinement, and proposed characteristics to be tested include geometry, size, and location. Now, obviously, one of the controls you'd want to test this against are actual windows, but then you have the problem of what are they looking at? I mean, we would have a problem with having the crew look out at a university parking lot. So, hypothesis 3, circulation patterns. A modular traffic pattern that creates a circulation loop will elicit functional and crew interaction differences from a non-loop tree pattern or dead-end pattern, such as existed on Mir and exists on ISS. And these differences include increased social action, positive or negative, and efficiency in response to emergency egress and access and normal operations. Hypothesis 4, physical and perceptual order. A habitat with physical order and visually clean appearance will increase work output and positive effects in crew function, mood, performance, and productivity. So here on the lower picture is the US Destiny Lab on ISS, and the irony is that the astronaut in the Hawaiian shirt has the most visually orderly element in the whole picture. So our expected results are that we will validate the fully operational modifiable space analog behavioral laboratory. The series of experiments will demonstrate the utility and flexibility of performing behavioral studies in a modifiable analog laboratory facility. It will also facilitate a new paradigm of behavioral research that moves beyond passive observation and the collection of expert opinions from so-called subject matter experts. Because one of the things we've run into time and again is that the people in the bureaucracy will say, well, we can just put together some subject matter experts and they'll tell us what to do. And we don't need to do any experiments because you've asked the questions and now we can put those to the subject matter experts. But, you know, where do the subject matter experts get their knowledge from? That's an unexplored area. And if you probe very deep, you don't find much far too often. And the lunar daytime will provide a heretofore unavailable degree of physical manipulation of the living environment that will lead to more definitive and complex mission simulation research, as well as provide for synergies between joint interdisciplinary efforts, such as space architects and behavioral researchers from sociology and psychology. Okay, I think that's the last one. Yes.
Questions?
Yeah.
So the usable volume on the ISS compared to a terrestrial analog is huge because of the weightless conditions give you access to the full volume. If we're on the lunar surface with 1/6 G,
is the analogs that we developed for ISS a better approximation, or those for Earth a better approximation? And how do you think that should be scaled?
Well, I have talked to a number of astronauts and also the psychologists at JSC about the extent to which the experience of microgravity affects visual perception. And there really isn't any agreement. I have heard anecdotes that when you're in microgravity, the environment somehow seems bigger. Other opinions that there's no difference at all. So it's one of these areas that's completely unresearched. I would say that since we're on Earth, we have a 1G environment, and the gravity in 1G, I mean the 1.6G environment on the moon provides at least the fact that things fall down, and if you put them down someplace, they'll stay in their place. I would say that doing these experiments in 1G is the best we're going to have until we can do experiments in a comparable habitat on the moon.
Other question?
Madhu?
David, I also think that the work that Mike Gernhardt is doing on the next step suggests that we already use a up and down on station. We know the floors, the patterns on the top and the bottom, ceiling and floor are different. But the question to you, Mark, is for a long time we've had vehicles that fly underwater, that go on the air, and for long lengths of time. Do we have anything, do we correlate our modules and designs to anything of that sort? Do we get any data out of those?
Well, Madhu, data, you know, there's very little work that's done to address the issue that this is about, which is how do we define what is a good design for a space habitat versus what is a not good design, you know. And while there may be some techniques or models that we can apply, that we can think about applying, no, the answer is no. Carol?
No, there were people waiting at the back.
Oh, okay.
Which one? Okay. Who was the one that had the hand? Who was the one? Okay, so you go. Who was the one? Okay. You? All right, we're wasting my time.
Okay, sorry. Is this working? Okay. I just have an experimental question. You talk about these psychosocial factors or whatever. You're measuring a reduction in stress, you know, depending on the configuration of the windows. What exactly are those factors? I'm just curious.
Well,
I guess how do you measure stress, I guess?
Well, there are a variety of modern instruments that basically work off of measuring galvanic skin resistance. There are observational techniques. We have a PhD in psychology, Cheryl Bishop, who just went emeritus at Texas Medical Branch in Galveston, who is leading that aspect of the work. And I'm really more of the sort of the project manager and instigator. But we do have a whole team of social scientists who are involved.
All right, thank you. Are you introducing us?
You've done 3, I'll do 3.
Yes, good.
See, drop the mic.
Yeah.
Thank you.
It's okay. Yeah.
Yeah, oh, good. Okay, so the next speaker is Valentin Pickle. That's good. Okay, anything? Lunar South Pole boulders and boulder tracks, implications for crew and rover traverses.
Thank you very much. Where's my clicker? One. Thank you. So during the last couple of days, we heard many reasons why we're interested in going to Lunar South Pole. One of them being the presence of PSRs we would like to explore. We also heard from speakers like David Kring and others that lunar South Pole is potentially challenging in terms of terrain. So the fundamental question that we ask ourselves at the moment is, how trafficable is the lunar South Pole? And one specific question would be, what are the geomechanical properties of the South Polar regolith? Another question could be, can you derive these properties locally, so at the South Pole, instead of using values that have been derived at equatorial sites, such as the Apollo sites or survey or lunar COD sites? You can imagine that it would be nice to confirm that these values that have been derived in situ during the Apollo missions, for example, are also valid for the South Pole before we go there. A more specific question could be, can we explore this on the South Pole with a crew or mobile assets, for example, the LER, Lunar Electric Rover? As David Kring mentioned on Tuesday, having a mobile asset on the surface would drastically increase the science output of a mission as crew is more mobile to move around. So what we like to achieve is high mobility, as you see on the left. What we like to avoid is getting stuck in soft soil, as you see on the right, happened to Spirit rover on Mars. And in fact, on the moon, one of the lunar COD rovers, which had a nominal sinkage of about 2 centimeters, sank down to 20 centimeters locally. And the LRV, Apollo 15 LRV, actually got stuck in a layer of soft soil and had to be retrieved by the astronauts manually. And these kinds of incidents highlight the fact that we have to be smart about trafficability at the South Pole. The tool that we use to better estimate these properties at the South Pole are rockfalls. You see an example here. A rockfall is a boulder that rolled, slid, or jumped down a slope, covering a track. You can see that track quite clearly here. You can imagine that a soft soil would result in a deeper and wider track, whereas a stiff soil would result in a more narrow, less steep track. The thing is, before we can actually analyze these tracks, we have to find these rockfalls in satellite imagery. So usually it takes about 30 minutes for a human to go through one single image to find rockfalls, which is quite painful as we have to scan through thousands or hundreds of images. So what we did, we applied some previous work from last year where we use a convolutional neural network to automatically detect and map rockfalls in NAC imagery. And we did this, applied it to images from the South Pole, more than 2,000 images, summing up to more than 200 billion pixels in total. And all of this took only a single day to perform, which is quite fast. And this is possible because the network only needs about 5 to 10 seconds per image compared to the 30 minutes that an experienced human operator would need. And by doing so, we found 79 rockfalls at the South Pole from the pole up to 85 south. And 58 of them actually right on the rim of Shackleton Crater or at Mons Malapert here. The red dots indicate these locations where we found rockfalls at the South Pole. This tool is going to be available on the awesome Moontrack platform very soon. So if you're interested in applying these tools, this kind of tool for your own research, you will be free to do so in a couple of maybe weeks, hopefully not more than months. All right, the first step of the analysis is then to compare the track appearances across the different regions. So we took our South Polar boulder tracks on the left bottom, lower bottom side of the slide and compared them to tracks that we previously found in previous work in pyroclastic deposits, Mare and Highland regions, you see in the middle of the slide, and also to PSR tracks that we found located on the bottom right of the screen. And what we find is that these tracks appear to be very similar across the regions, which indicates that the geomechanical properties across these regions might also be quite similar. The second step has then been to quantify our observations using the concept of, or the theory of static bearing capacity. So we applied equations from Terzaghi and Hansen to do so. You can imagine a block that sits on the surface of the moon with a certain weight, and then this weight acts on a certain area of the soil. So you have a force over an area which gives you a pressure. This is called the bearing pressure of that object. And if you imagine that this soil holds that boulder and counteracts the downward pressure, you could call this the bearing capacity of the soil. And bearing capacity is interesting because we can use it to estimate the sinkage of landers, rovers, or crew. We can also use it to estimate the behavior of foundations. So if you're interested to place a heavy telescope on the surface of the moon, you might want to consider bearing capacity, for example. Another parameter that we look at is the rolling resistance of the regolith, where we use equations customized from David Carrier's work. You see on the right side a plot of a cross-section of a sphere or a boulder, a round boulder on the surface, where a boulder is driven down slope by its weight and the slope angle. And as we observe that there are boulders on the surface which stop rolling on inclined slopes, we can infer that there is a force that holds these boulders back, which is the rolling resistance. And knowing about this force can help us to better estimate rover energy consumption, and can also help us to better understand how rovers are able to climb slopes in general. All right, some of our results are shown here. Specifically, the bearing capacity as function of depth at the lunar south pole. The x-axis shows bearing capacity in kilonewton per square meter, and the y-axis shows the depth from the surface down to 5 meters. And the line that you see is a general bearing capacity envelope that has been derived for highland, mare, and pyroclastic regions in previous work, and that has been validated using in situ Apollo and lunar code data. And these little triangles in the upper part of the plot indicate our south polar boulder tracks, and you can see that most of these triangles fall either on the envelope or on the right side of the envelope, indicating that the capacity values are equal or higher in these regions, which is a good sign for us. What we also observe is at the bottom left, our coefficient of rolling resistance is about 0.05, which vaguely corresponds to the resistance that a standard-sized wheel encounters on large cobbles. All right, what we can also do is we can apply our values, our measurements to as a function of slope angle. You see on the x-axis now is the slope angle, on the y-axis is the bearing capacity again. And you see that if you go on steeper slopes, you have a lower bearing capacity, and quite drastic decrease of bearing capacity. And this enables you to plot bearing capacity as a function of topography. Here's as the lunar south pole, where white colors indicate higher bearing capacity values and blue colors indicate lower bearing capacity values. The black spots are PSR regions. You can imagine that this kind of map product might be useful for mission planners or engineers to understand whether their rover, where we know the weight and the contact area with the ground, might be able to manage a certain traverse, or if there might be some sinking-related issues along the way. You can also imagine that this map would be useful to understand if there are potentially targets, scientific targets in the region that might be easier to access than others based on the bearing capacity. So one could, for example, combine this particular map with a slope map or other hazard maps to get a better feeling for future exploration in general. All right, with this I would like to summarize that talk. So we used a neural network to detect 79 rockfalls in the South Polar region. We then compared the track appearances across all these regions and found that they look very similar, suggesting that the mechanical properties are also very similar across these regions, which is a good sign. And we then quantified our results, our measurements, and found that these numbers actually support that initial finding. So we should assume that landers, rovers, and crew would not encounter any sinkage-related issues at the South Pole, for example, at the rim of Shackleton crater. So it's also a good sign. And then we summarized all these insights into a number of map products. One of them have been showed here. And I hope that this kind of product might help to support the ongoing planning for future missions and in general. However, there's one thing that I would like to note, based on the incidents that I described before. We have still some knowledge gaps about lunar storm mechanics, and this might be a good point in time to think about how the Artemis or CLIPS missions might help us to advance our knowledge in lunar storm mechanics, and how we could use that advanced knowledge to minimize the risk of future missions on the lunar ground surface. And if you're interested in some of the resources that I showed, feel free to scan those QR codes if you can do so. And those will directly point you to the respective resources. Thank you very much.
Any questions?
Do you think that this track data indicating the similarity with other regions also may suggest that the water density may not be as high, or that the constituency of water in the regolith is not affecting at all the surface properties?
Are you referring to PSRs or in general?
Well, in general, near the pole, because it's postulated, Paul Sputis talked about,
Yes.
you know, much higher elevated water, even in the non-PSR regions.
That's a very interesting thought. What we can do at the moment is we can observe these tracks and we can only see that they are similar. So this is something which would be interesting to investigate in situ once we are on the surface.
I mean, it looked like the strength was even higher than you would expect. Is that not right? For the yeah, you're off to the right of the line.
Yes.
And you know, might that not be the effect of water, you know, or ice within the pores and things like this? That would, you know, make it a frozen ground instead.
Yeah, that's
of,
in sunlight. So those are values taken in sunlight
with
conditions.
a very high angle of sunlight. I don't know the average temperature or the effects. You know. Yeah.
So I would not expect
Very low angle of sunlight. Yeah.
a high influence of water on that.
I don't know who it goes to.
So one more, which I'll take. So you were talking about experiments that you would fly on clips, soil mechanics experiments. Do you want to, you can have 30 seconds to say what you mean.
I think there are a number of things one could do. The easiest thing would probably be to document any interaction of a lander or human with the ground, taking pictures, videos, and so on. For example, if you have a robot that drives a certain traverse, you could always have a camera pointing backwards, take a picture of the track to get a line measurement along the traverse. That would be very interesting to see. One could also deploy a penetrometer, as Lunacod did, which is also very useful data. Those are probably very cheap and very simple options that could just be added to a CLIPS mission or a manned mission to the moon.
Okay, thank you.
Thank you.
Next talk is virtual reality interfaces for surface robotics from the Gateway, and the talk will be given by Michael.
Oh, right here. Okay. Yeah.
Okay. 12 minutes.
I don't think this is the. Actually, I know it's not. This isn't the right one.
So it looks great.
Yeah, it does.
We'll go ahead and give it anyway.
There we go. That looks good. Thank you. Okay, actually, Mr. Okay, so hello everyone. My name is Michael Walker, and I'm a computer science PhD student working with the NEST team at the University of Colorado Boulder with Jack Burns. And today I'm going to talk about an alternative method for surface telerobotics using virtual reality interfaces. So, as we all know, there are many instances in which our robots are located in some far away place relative to their operators, such as fighting fires in the wilderness, exploring the bottom of the ocean, or, as we like to focus around here, robots crawling across the surface of planetary bodies. And what's really exciting in this field is that there seems to be some sort of advancement almost every day that helps these robots better explore our universe, such as hardware advancements that let these robots traverse previously thought to be impassable terrain, or we have software advancements that let these robots navigate complex environments despite long communication delays using autonomous systems. But what about advancements in the interfaces that these operators are using to interact with these robots, whether direct control or supervisory control? Well, for the most part, it looks the same. It's using the same technology, these flat two-dimensional screens that we've had for decades, really, and they're doing the best they can to filter down three-dimensional data to 2 dimensions. So it kind of begs the question, how can we leverage these newer technological leaps we've had in other fields to better our interaction with these robots? and utilize this rich data that they're returning back to us. Well, one potential solution that'll be posing to you guys today is these virtual reality headsets. And as many as you know, one really major benefit to these headsets is that they let users see with depth. Each eye has its own lens and gets its own image, which gives the ability to see in 3D, and also have a wide field of view. And paired together, this provides a really strong sense of immersion where users can feel like they're in these virtual environments, or in our case, the real world. For previous research has used the same method, but with real cameras. So if you attach a camera to a robot and then stream the dual stereo video streams to the headset, you can feel as if you are looking out of the eyes of the robot, as if you're there in some faraway place, which also lets the users feel like they're embodying this remote robot. So with this idea in mind, our team really wanted to further explore this kind of more nascent design space, and especially in the field of space exploration and surface telerobotics. So we started by creating our own little virtual reality simulation testbed, where we have a virtual lunar surface, and we modeled our own rover, which we then could pilot along the surface of the moon for simulations. Here it is. And what's nice is that these headsets work just out of the box with these high fidelity, I'm blanking on the word, but physics simulators, which are game engines, which allow for a really rapid development pipeline, which is nice for us developers. And we can simulate things such as third-person control, traditional first-person control, looking at the from the viewpoint of the robots from first-person on traditional monitors or VR headsets. So here we can even sync up the user's head rotations to the control of the robot's camera, allowing for a more intuitive, natural piloting experience as if you are the robot on the surface of the moon. And these virtual reality headsets, again, we render the scene twice, once for each eye to give this feeling of 3D. So now that we have this, we can project things with depth, we can also add virtual augmented reality imagery to the scene as well. And I don't just mean two-dimensional widgets, as we're so used to with these interfaces, but we can add augmented reality that actually integrates with the environment itself, where we can have an occlusion. And so this is, again, leveraging this depth that we can use for these VR headsets. Stick our hand through these things. Yeah, it's pretty cool. So we can add three-dimensional virtual imagery to these interfaces to, again, have a more rich, progressive interface for controlling these robots. Okay. So knowing that we have just these inherent benefits with this VR technology, we wanted to run a study to compare what benefits we have by just switching out these traditional interfaces, these monitors here, with virtual reality headsets. We ran our own experiment. So it was a 2x1 experiment where we either had our standard interface, again, these monitors, or a VR interface. We kept everything else the same. We didn't change the controls in the tasks we had the users perform. We didn't add any head tracking or hand tracking, just to really isolate just the addition of the VR headset versus monitor. This is within subject design, where subjects used or completed the tasks twice, once with each interface, but we randomized the order. We had 12 subjects, 10 male, 2 female, with an average age of 22. And we evaluated, our tasks we chose were assembly tasks, simply because we have these exciting new ideas in the pipeline of potential uses of these robots on the lunar surface, such as assembling far-side radio relays. So here's a little bit more about our experiment here. We used an industrial-grade fetch mobile manipulator robot right here, which one would actually see in a factory floor to do fetch tasks or assembly tasks. And we attached a stereo camera and piped its information to a standard commercial VR headset, an HTC Vive here. And we ran our experiment in our lab space and controlled for lighting, so we didn't provide unnatural depth cues from the lighting ahead or above. Here is a subject actually running this experiment here. All videos are sped up just for the sake of time. And I'll go over what some of the tasks were next. So one of the tasks we ran was an object stacking task. And here we started by having users stack cubes, which is the easier of the two parts here. And we were looking at our main metric of efficiency, how quickly could they complete this task using either interface. And then we'd move on to the harder task, which is stacking these cylinders, which were much more difficult since they're skinnier, taller, etc. Another task we looked at was object sorting as well. So in a cluttered environment, users had to then sort out the blue-hued objects from one side of the table to a partition side. Again, we were looking at the same efficiency metric as we were before. So next I'll move on to some of these results. So this is looking at time to complete. So the lower value, the better, because it just means they finish the task faster. So we have significant results with the VR headset with stacking the cubes, marginally significant results with the cylinders, again with the VR headset outperforming our standard interface. For time to complete with sorting, we didn't quite get significant results, but we can start to see this trend still appearing here. And for interface preference, we asked users which interface subjectively did they just prefer to use overall and what made the task easier, and we have the significant amount of participants choosing the VR headset over the monitor. And again, this is just using out of the box, switching the interface to the VR headset. We didn't even leverage all the additional features that we can use with this technology, such as head tracking, where we can, again, sync up the user's head movements to the robot's camera, or hand tracking to allow for a natural experience. Users can match the end effector of the robot with their own hand for more precise movements. Full body tracking, for with these VR headsets, we're not just tracking the rotation of their heads, but we can actually get up out of our chair and move around the environment, which future interfaces could and probably should leverage in one way or another. And we can add assistive augmented reality, which I touched on before. And we can also think about integrating things such as point clouds. So for example, if I'm driving across the surface of the moon and I'm the operator and I'm seeing out of the robot's eyes and I want to stop and see, is my wheel close to a hazard on the ground? But I look down and the robot is occluding my view. What if at the same time I'm using LiDAR to create a point cloud as I'm driving, and if I have some idea of where the robot is relative to this point cloud, which I probably do, I could then switch to a different interface mode, step outside of the robot's eyes, and then walk around the point cloud in a model of the robot and like bend down and take a look to see how close this wheel is to a hazard. I could then maybe pilot the rover from that view or snap back in to the robot's point of view. And again, these are just examples of ways that we can combine different features for these headsets to create a more rich, higher performance interface for these robots. These are all things that our team are hoping to look at in the future. And I'm an intern at JPL this summer, and I'm happy to report to you guys that I've seen plenty of projects actually adopting the use of these VR headsets or augmented reality headsets. But they're typically in the capacity of simulation, playback, or analysis of previously recorded robot data in this more secondary nature. But I think it's time we start looking at using or in discovering or investigating how to use these headsets for primary operation or at least supervision of these robots. And not to mention, we have the gateway that's going to be in place, which will allow for unprecedented bandwidths and lower latencies, where astronauts could potentially control these robots from the gateway itself instead of having to travel to the surface of the moon to feel like they're on the surface, instead they can body themselves as a robot. And finally, prepare for Mars, which is, again, our primary goal most of the time. And it's not hard to imagine that these astronauts would be able to put on a VR headset and feel like they're in some remote hazardous location as a robot from the safety of their enclosure, be able to pick up a sample and look at it as if they're there. And not to mention just that, but as a fail-safe for when autonomous systems, if they fail, or more likely when, they'll have a more powerful way to navigate these robots out of safety or back to their home base, since they're such valuable assets. So with that all in mind, our team will hopefully be able to show you more interesting, feature-rich designs in the future, as well as experiment results in future forums to come. And above all else, hopefully maybe I sparked your imagination for what this type of technology has in store for the future of space telerobotics. So with that, thanks for having me. It's a pleasure to be here.
Hi, you spoke a little bit about latency, and I was just curious, how you think the results of your initial tests and preferences for the standard monitor versus VR will change with a much larger latency.
And that's a great question. So I think there's different methods of approaching this because, realistically, we won't be able to get near zero latency, at least for now or in the near future for these types of interfaces. But we can still do work now that can help us prepare for the futures when we can get close, maybe. Or we can create a design in a perfect condition of what combination of features gives us the best performance. And then from there, we can suggest to NASA in future designs what latency we do need. Or maybe we can back out features that can maybe co-align with what we have available hardware-wise for latency drawbacks. But really, it's finding the optimal design first and then maybe working backwards to make more intelligent suggestions as to what we should be aiming for in some way. But yes, so it is an issue, but it's something we definitely have in mind as we're doing these types of studies. Thanks.
My question's along a similar line, but have you thought about using this same technology to augment human exploration? So you've got an astronaut on the moon, using the VR technology, get your scientists on Earth ground, the orbiting stations to then assist with the science aspect of lunar exploration.
Yeah, so are you thinking more along the lines of they could feel like they're on the surface with the astronauts themselves in some way, or just any old way, just using this stuff?
That is one way, but also has exactly the same as you're doing the robotics, but putting those cameras on the astronauts themselves.
Oh, yeah, I see what you're saying. No, that'd be another interesting way to do this. And actually, our team is we have close ties with the Colorado first response teams who actually go out and fight forest fires. And we're doing studies, or we're hoping to team with them so we can see how we can help with command centers using AR/VR technology, as well as humans on the field with mixed human-robot teams, and how we can bring all this technology together to hopefully bring the interface of the future for this type of work. So yeah, no, there's so many different ways we can pull this together, and that's just one aspect that you mentioned. So it's pretty exciting.
Is there, well, yeah, just very quickly. So this is Back to the Future for me. In the late 90s, I did some experiments in Antarctica using head-mounted display, head-tracked, on an underwater vehicle.
Okay.
So maybe we could talk later.
Oh, I'd love to, yeah, definitely.
Thank you.
Okay, thank you, everyone.
Okay. It's the last talk of the day, and we know we've got the slides.
Can you all hear me?
Yep.
Great.
Okay, so impact ejector environment of an eccentric asteroid 3200 Phaethon, you can pronounce it. Right, you're on. I'll shout 1 minute at you at a random time.
Sounds good, and I got a timer on my end too that I'm watching. All right, thank you. So sorry I couldn't join you all in person. I hope you all are having a great forum. I know I'm the last talk of the session, so I will try to keep this well in the time range. Today's talk is going to be about a specific asteroid. Before I begin, I'd like to thank all my co-authors who both contributed to the work presented in this and then the paper that we had published earlier this year. This talk is about a very specific asteroid, but it's more generally about how we can learn about the evolution of airless bodies and the zodiacal cloud using robotic asteroid flyby missions. Additionally, eccentric asteroids like this one undergo different degrees of space weathering compared to their circular analogs, and so I'll briefly touch on that. So next slide, please. So 3200 Phaethon is a really interesting body. It's a B-type active asteroid. It's 3 kilometers in radius. It's the parent body of the Geminid stream, but it's one of the only meteoroid streams, and it's one of the strongest streams. That is, the parent body is thought to be an asteroid, not a comet, which is very interesting. It is the target of JAXA's Destiny Plus mission, which has on board a dust detector that has chemical sensing capability. And so that means that if it flies by close enough to this asteroid and it detects the chemical composition of the ejecta, it's actually directly sampling the surface material of the asteroid without even landing. And that's a really exciting and powerful technique that we're looking forward to. In this, what we'd like to do is predict the impact eject environment to understand how an asteroid's meteor bombardment environment varies through the orbit, and also better frame the ejecta measurements that will be taken by Destiny plots. And lastly, as you can see from the orbit, it's a highly eccentric orbit. It's like 0.88 eccentricity. Next slide, please. One of the interesting things that we have to assume, but that we can learn by going to the asteroid, is the ejecta yield. This governs both how much material is eroded from a body due to impact, and that material for asteroids is then contributed to the zodiacal cloud and re-impacts other bodies. But it also, the yield tells you how impact energy from meteoroids is partitioned into local heating compared to ballistic ejecta. There's a few bodies that we've flown by. We've never measured the actual yield, but we've inferred it with other dust detectors of other airless bodies. So, for example, the Galileo mission flew by Callisto and Ganymede and Europa and was able to estimate their yields, which is the ratio of ejecta to impactor mass, at something like 10 to the 3 to 10 to the 4, 1,000 to 10,000, which means that 1 gram hitting one of these icy bodies ejects something like 1 kilogram to 10 kilograms of ejecta, a lot of material, huge yield. But recent measurements at the moon have indicated that this fluffy Regolith surface at the moon has a much lower yield by orders of magnitude. And that might tell us that there's more heating from meteoroids than we previously thought. And so there's this large range of impact yield that we don't know exactly where asteroids fit onto this spectrum. And so for the rest of the talk, we'll assume it's lunar-like as a very conservative estimate. But one of the exciting things we can do with an asteroid flyby mission is determine the yield, and then that determines how much material the asteroids and the Kuiper belt, for that matter, are sourcing the zodiacal cloud and the dust environment of our solar system. So next slide, please. To predict the ejecta production, we use a dynamical model that's maintained by Peter Pokorny and colleagues that tracks a lot of different simulated orbits from a lot of different parent bodies. For example, Jupiter family comets, asteroids, Halley-type comets, and Oort-Cloud comets shown in the corners of this figure. And then we combine them all together using a normalized weighting from radar measurements at Earth. And this is an all-sky map of what we think the best estimate of the flux distribution looks like at 1 AU. This frame is centered as if you were on the windshield of a body orbiting the sun. This is a circular orbit, so this would be like the moon or like Earth, where the center is your ram direction, the parallel to your velocity vector. 90 degrees to the left is the direction to the sun. Again, this is like you're looking out, so the left view, the left window would be sunwards, and then the right view would be anti-sunwards. And you can see that there's a couple different sources of meteoroids that impact. The two brightest ones are from Jupiter family comets, to sit you roughly from the Helian, anti-Helian, sunward, anti-sunward. And then there's a couple other different distributions that have different velocities, and we'll see what happens as those get morphed from an eccentric asteroid. So let's go to the next slide. So that's the impactor environment. We then need to know how much material is ejected from these impactors, and we use the moon as a basis. So shown here is all of the LADI data that we have to date of the 6 months orbit, and that's the dust density distribution that we measured with LADI. And what we found was that it was highly asymmetric about the apex direction, the direction, again, of orbital motion. And that was because even though there's not a lot of grains that are running retrograde, so they're orbiting in roughly circular orbits, but they're going the opposite direction, so you get double the speed of your orbit as an impactor. There's not a lot of them, but they generate so much energy, they're able to eject a lot of material. And so that mostly dominates the eject environment at the moon. And so from these measurements, we were able to understand that the eject environment is pretty well understood by the sources of meteoroids that we had already known existed in the sporadic meteoroid distribution. The next slide, please. From there, we need to know how they're ejected from the body. And so we measured and inferred an altitude dependence from the moon, and so we then apply this to asteroids. And so we found it was an exponential distribution at the moon, and And we use the same, we can take this, and then in the next slide, please, we invert the altitude distribution, and we get a speed distribution. And that tells us now how much, how fast, and of how many at each speed particles are ejected from a body. Next slide, please. So we take all those lunar measurements, we take the dynamical model, we put them all together, and I just wanted to lay out the assumptions on how we calculate this eject environment. So we assume production of ejecta is identical to the moon. We assume it scales like existing measurements. It's something like the flux times the energy to an exponent of the impactors. We assume it has a power law distribution that extends down to 50 nanometers in radius. The grain density is some nominal silicate. For an asteroid that we model, especially this one, gravity is negligible compared to the moon. And so we assume all ejecta is unbound. And lastly, radiation pressure is negligible. So let's go to the next slide, please. And you can skip that one as well. Next slide, please. So one of the big differences and main differences for a circular orbit is this is just if we were to take what we learned at the moon and apply it to an asteroid, this is what the ejecta density distribution would look like. Instead of an exponential, which had to do with how gravity is pulling back down on that ballistic ejecta, we have something like Coulomb's law, it's 1 over r squared, and we get this nice lily pad looking structure where most of the ejecta is in the up direction, which is apex, that's from those fast impactors. So now what we want to do is take this nice circular case and then see what happens when we have this highly eccentric wild orbit flying through the meteoroid environment. So next slide, please. So on the right in the top is the flux map from before. It's this nice symmetric flux map from a circular orbit. And then on the left is the flux map we would infer or guess that Phaethon is experiencing. And so you can see it's highly morphed. The biggest color blob, if you will, on the bottom left of the Phaethon is that helium source on the left in the circular. But what's going on is that Phaethon is ramming into that helium source. It's got a much higher radial velocity towards the sun, and so it's running into particles that are going outbound. And so it gets accentuated there. And then these two central peaks that are in the center of the map on the right, they get moved a little over to the left again because of the vector addition. And all this is to say that instead of the circular case where the flux varies by maybe an order of magnitude or two, for Phaethon, it's highly asymmetric and it varies, the flux varies order many orders of magnitude, something like 6 orders of magnitude. So let's go to the next slide. So we can take the flux and the speed and predict what our eject environment looks like. The bottom right is now the nice lily pad for a circular orbit. The bottom left is Phaethon's orbit. And now instead of most of the ejecta production being dominated by the apex and it's going out in front of the asteroid, now most of the ejecta production is at 1 AU, is heading towards the sun because it's ramming into the dust so much faster on that side. So let's go to the next slide, please. So we can take those measurements and there's predictions, and then we can fly Destiny Plus through it and make some predictions on what kind of structure we think we would see. And so shown in it's maybe a little hard to see for the darker lines, but the lower lines are flying kind of behind on the anti-sunward side. This frame, the sun is to the left, apex is roughly in the vertical up direction. Sun is minus x direction. And so depending on where you fly by, this on the sunward or anti-sunward and your distance, you can get different impact rate profiles, and the structure and the shape of that profile really well encodes the structure of the ejecta distribution. And so from even just one slice through, it's like a Langmuir probe in that you can learn so much about the structure of the ejecta cloud with just one flyby. Additionally, even with these super conservative numbers, we used a lunar ejecta yield, which is the lowest thing we've ever seen, and it's most likely not representative of asteroids. They're much likely more coarse and have higher impact yields. And even for that, with close flybys, we get an appreciable number, something in the 10s to 100. And each one of those is a nice little chemical sample of the asteroid's body. So in the worst case scenario, we're going to get dozens of chemical samples of Phaethon, which is a totally exciting and revolutionary measurement. Next slide, please. So the last little piece I wanted to talk about was just how the orbit really modifies its environment. So now this is, before we were always looking at one AU case, but this is kind of a day in the life or an orbit in the life of the asteroid. And on the left is the flux distribution, and you can see how as it's far at aphelion, it's traveling, and it's most of the flux coming from behind it, and then as it goes towards the sun, you're hit from the left side and the right side. And so the flux varies highly throughout its orbit. Next slide, please. And this is the last before the conclusion. And so what we can do is we can predict how much ejecta is being produced and how much is lost from this, and compare that to erosion rates, to how active the asteroid is, and then that could also be used to compare it to space weathering timescales. And so for this eccentric asteroid, the amount of material that's lost is something like 40 times the amount of a similar body on a circular orbit. And so we would expect at least 200 microns per million years to be eroded from Phaethon compared to a circular orbit. And so the eccentricity of the orbit is really important in governing how important meteoroid bombardment is compared to, say, solar wind sputtering and other space weathering aspects. And so the eccentricity should certainly be taken into account for comparative studies. All right, last slide, please. So in conclusion, the ejecta cloud is very asymmetric because of the eccentricity. Phaethon sheds about 40 times more material than a circular orbit, and this provides us context for how asteroidal space weathering is compared across different bodies. And we would expect Destiny Plus to reveal, with even just one fly, by what an asteroid's impact yield looks like, what the regolith composition is and the composition of a B-type asteroid, and it would allow us to test our models of the zodiacal cloud. And so we have this in a paper that came out earlier this year, and with that, I'm happy to take any questions. Thank you.
Wait, just a second. Can I say something? I just want to say something important here because I'm responsible for the agenda. And the reason why we put this one here is because this is sort of a little bit like planetary defense. This is crew, right? You know, we're talking about crew habitation and all of that. But can you imagine that we have all these meteorites coming to Earth, and then we'll see them as shooting stars. But if you are in the moon, they're a serious hazard that we need to consider, right? So that's my comment, so we have that perspective.
Any questions?
I didn't mean to shut everybody up, but I just wanted to say that from that perspective, you have to consider that, okay? So it's just so it makes sense in the agenda also as the habitation. Yeah. All right.
Well, if no questions, can we just thank the speaker one more time?
All right, thank you, everyone.
Okay, so that's the end of the session. We have a 15-minute networking break. If you're quickly on your computers, the SpaceX is 27 seconds into launch, if you want to watch that. And we're starting again in the main room with the plenary at 3:15.